Hello and welcome to lecture 19. We are discussing our third module for design concepts. In last lecture, we were discussing about our free vortex concept, and we realized when we are having say free vortex kind of design where you will be having blade to be highly twisted. And in order to address that high twist, we are having different configuration. It says we can take Cw into r to the power n equal to constant, where we have seen that's what will be varying between some range. The n, that's what is varying from -1 to 2. We can say when we are discussing about the design of axial flow compressor, in order to take care of what is happening near my hub and near my tip region, this exponent we are taking to be in a higher number. And in order to compensate what losses we are getting in sense of loading, in particular mid section, these exponents we are taking that to be a lower value, maybe in the range of 0.8. So this is what is one of the philosophy what we have discussed. Then we were discussing about the application of our vortex equation. What it says, in order to have that to be applicable, it need to satisfy what assumptions we have made. So if we consider say for high bypass ratio fan, say exit of my flow coming out from fan which is entering inside my core engine, that's where my pressure rise requirement is comparatively low. And if we are considering on upper portion of my blade, where my radius it is changing, my speed is changing, that's where we are considering our loading to be higher. My pressure rise expected in that particular region is higher. If that's what is your case, then you need to modify your vortex energy equation in such a way that you need to have consideration of variation of stagnation enthalpy with the radius. Then we started discussing about different approaches for the vortex selection. And the recent approach we have assumed in which we are considering our total enthalpy, that's what is remains constant along the span. We can say my H0 that is not varying along my hub to shroud, or we can say our work input that's what is remains constant. And we are considering arbitrary whirl velocity component distribution. So we have seen at the entry of our rotor, or say at the exit of the stage, previous stage or previous stator, we can say my Cw1 that is given by this formula, say A into r to the power n minus b by r. We can say at the exit of our rotor, that's what is given by A into r to the power n plus b by r. Now here also we are taking different numbers. Say this exponent what we are taking, and we discussed in last lecture when we are considering our n equal to 0, that design approach it is called exponential design. When we are considering n equal to 1, that's what we are referring as a constant reaction design. When we are considering our constant A equal to 0, that's what we are defining as a free vortex design. And if we consider my B equal to 0 and n equal to 1, that's what is defined as a force vortex design. Sometimes people they are considering that as a first power design. So today we will be discussing about how do we use this exponent for our design calculation, and what all will be the impact on our calculation for flow angle, for the calculation of our degree of reaction. So let's consider, before going into detail, what we have discussed in last lecture. We are having unknowns like constant A and B. These constants we are calculating based on our formula for degree of reaction and my stage total pressure rise. If that's what is your case, and if I'll be simplifying the equation for my degree of reaction and work done, we will be getting the value of constant A and constant B. And we have discussed in last lecture, say that's what is a function of my radius. My A, that's what is varying with my radius. My B also is varying with my radius. And it is also a function of my peripheral speed at the mid station. So conventionally, what all books we are referring, if we go through, they are doing the calculation at the mid section. So calculation of mid section, that's what is very important. So what all calculation we also will be doing, initially we will be doing those calculation at the mid section. And then after we will apply the logic for the variation of our whirl velocity component from hub to mid section and from say mid section to tip. So we must have the details what is coming in sense of my flow angles, in sense of my velocity components at the mid section, that need to be known to us. If not, then we need to assume. So let's move, say we consider first say n equal to -1. We can say that as a first order design. Okay. Now my whirl component, as we have discussed, my CW1 and CW2, that's what is given by this equation. And from our fundamentals, what we know, in order to satisfy the radial equilibrium equation, we need to have our work input or my H0 that need to be constant along my span. My axial velocity also remains constant from hub to tip. And we know my CW into R, that's what is equal to constant, that is giving me free vortex concept. So we can say if I will be satisfying all these equations, all these three equations or three conditions, I say that's what is satisfying my radial equilibrium equation, and that's what is compulsory. Okay. So if we consider, say here, if I'll be putting my n equal to -1 in this formula, that's what is giving me my CW into R, that's what is equal to constant. So you can say that's what is in line to what we are assuming as free vortex concept. And if we made the assumption, say like my H0, that's what is constant, then in my equation I can write down, this is what is my formulation. It says Ca dCa by dr plus Cw by R d by dr RCW, that's what is equal to 0. In that equation, if we will be putting our Cw into R equal to constant, it says my dCa by dr, that's what is coming to be 0. The meaning is my axial velocity remains constant. Now you can understand, if I am taking my exponent as say n equal to -1, that's what is giving me my free vortex design concept, and that's what is satisfying all the three conditions what we are looking for satisfying of radial equilibrium equation. So this is what will give you idea, this is what will give you say method in order to calculate how my flow angles, degree of reaction and work, that's what is been varying along my radius. So we can say n equal to -1, that's what is giving us my first order design. We can say that's what is say my free vortex kind of design. Now let me move to the next. Suppose if I consider my n equal to 0. So in this equation, if you look at, that's what is say my CW1 and my CW2. And as we have discussed, what is our requirement? I need to satisfy my radial equilibrium equation. And in order to satisfy my radial equilibrium equation, I need to have satisfaction of my H0 equal to constant. I need to have my axial velocity to be constant, and I need to have my Cw into R equal to constant. If these three are meeting, then we can say we are satisfying with radial equilibrium. If you recall, I was discussing say two of the parameter. If we know then it will be possible for us to do the calculation for third parameter. That is also one of the way to use our radial equilibrium equation. So here in this case, if you recall, say we are assuming our whirl component, that's what is varying here by certain proportion, we can say by this equation. If that's what is your case, and if I'll be putting my n equal to 0, my Cw1 and Cw2, that's what I can write down as say A minus B by R and A plus B by R. Now you can understand this is what is not giving me the satisfaction of my say free vortex, say Cw into R equal to constant. But as we have discussed, we can do the calculation of other parameters. So let me write down the equation. This is what is our equation. So we can say my variation in axial velocity, that's what can be calculated by using this formula. Just understand one thing, this is what is representing our situation where my Cw is changing, that means my axial velocity may change. Okay, so let's have a look at, suppose if I consider at the entry my Cw1, that's what I'm writing as say A minus B by R. So in this equation, if you look at, since my Cw1 or Cw, that's what is changing, then I need to do calculation what is happening with my axial velocity. Okay, so if I'll be simplifying this equation, that's what will be coming as 1/2 dCA square by dr plus A minus B, A by R minus B by R square into this formula. Okay, if I am simplifying this equation, this is what will be giving me how my variation of axial velocity, that's what is happening. Now in order to do the calculation how my axial velocity is varying, I will be putting my limit from say my midsection to any station R. So I can say this is what is my integral form of my axial velocity, and this is what is my integral form for my variation in radius. If we are simplifying this equation, we will be getting at the entry of my rotor, the axial velocity, that's what is varying, it is in sense of my say axial velocity variation at the midsection or my magnitude of axial velocity at the midsection, and this is what is a function of my radius. Okay, we will not go into detail in sense of derivation because this is what is my design course, and in design course maybe with using your pen and paper try to calculate this CA1 what you are getting. Okay, so it says CA1m, that is nothing but my axial velocity at the mid station at the entry. Okay, and my CA1, that is nothing but my axial velocity at any station. Okay, so you can understand at mid station I know my axial velocity, suppose. Then I can calculate how my axial velocity is varying along the span at the entry of my rotor by using this formula. Okay, now if we are considering what is happening at the exit of my rotor, so in line to that we can write down the equation for say exit velocity or exit axial velocity, that is also in sense of CA2 at the mid station, and this is what is in the form of say my radius. So if we try to look at here, just understand like this is what is giving a different kind of feeling. What it says, we are having not satisfaction of our radial equilibrium. What is the reason? Because my axial velocity at the entry and exit, that's what is not remains constant, it is varying. Okay, and that's what is not satisfying my radial equilibrium equation. Now the question must arise in your mind, say if it is not satisfying the radial equilibrium, then what need to be done? Okay, so that's what we will be discussing very soon, but you can understand when I am considering my exponential design in which I will be having my axial velocity at the entry of my rotor and my axial velocity at the exit of my rotor, that's what is not same, it is varying. Now immediate question will come, what is happening with my degree of reaction? So if we consider here, say from my fundamental equation, I can write down my Cw1 and Cw2, and the degree of reaction equation, if I will be putting this Cw1 and Cw2, that's what is saying my degree of reaction, that's what is varying with my radius. Okay, so my degree of reaction, that's what is varying with my radius. So let's try to look at here what is happening, what all numbers we are discussing. What we have discussed, we are having two approaches where my n we are considering equal to -1, and when n we are considering to be 0. So if you look at here, this is what is representing along my span what is happening, and this is what is representing the variation of degree of reaction. So you can say somewhere on downside you will be having your hub, and somewhere here you will be having your tip. Just do not get confused, this is not hub and this. So this is what is normalized with respect to my mid section. Okay, so if we look at considerably here, so here if we try to look at, suppose say if I am taking my n equal to -1 condition, so you can say this is what is giving me my degree of reaction to be 0 at one station. Suppose if I will be extending that line further on my y axis, it says it is giving me my degree of reaction to be negative. Same way, if you are considering my n equal to 0, it may be possible further extension, that's what will be giving me my degree of reaction to be negative. So we can say the degree of reaction, that's what is a very important parameter, and as we have discussed, that's what is a thermodynamic parameter in order to check the diffusion, that's what is happening in my axial flow compressor. Okay. Now with this, the next step, that's what will be coming is, say let's consider my n equal to 1 condition. So when I am taking my n equal to 1 condition, say in this formula, if I will be putting, say I am simplifying this form as, say I am assuming my R into Cw1 equal to some constant K1, and I am assuming my R into Cw2 equal to some constant K2. Okay, so if we consider here, and if I will be putting that in my work done equation, that's what is U into Cw2 minus Cw1, that's what is coming to be constant. Okay, so we can say this is what is my situation where my H0 is constant along my span. Okay, what we know from our velocity triangle, we must know like what will be my variation of beta 1 and what will be the variation of my beta 2, because we are interested in calculation what is happening with our degree of reaction. So under this condition, when we are taking our n equal to 1, we will say the degree of reaction simply will be kept in terms of my delta beta or beta 1 and beta 2. Suppose say if I am assuming my axial velocity to be constant. Okay, if this is what is your case, just realize one of the condition we are putting Cw into R equal to constant, that's what is my one condition. And what we are assuming? We are assuming our axial velocity to be constant, so that's what is my second condition. If that's what is your case, you can understand you are able to calculate what is happening with my stagnation enthalpy or my work done. So as we have seen, out of 3 constants, if 2 constants are known to me, my third constant we can calculate. Okay, so here my degree of reaction we can say that's what is coming in sense of 1 minus k by r square, where k, that's what we are writing as k1 plus k2 by 2 omega. The value of this k is always positive, and that's what is increasing from hub to tip. Okay, now here in this case likewise, say my Cw square by r is always positive, that's what is giving me my static pressure rise, it is happening from say root to tip or maybe from hub to shroud. Okay, so we can say my static pressure rise, that's what is given by constant minus k by 2r square. So here if we try to look at, say, this is what is my situation. We are talking about different values of n. We are talking about the exponent value of n. We say we are considering n equal to minus 1. That's what we are discussing as, or we are selecting that as a free vortex design. We are taking our n equal to 0. That's what we have considered as a exponential design. And we have taken n equal to 1 condition. That's what we are considering as a first design approach or first order design. If that's what is your case, you can see this is what is representing how my degree of reaction, that's what is varying. Now, interestingly, as we have discussed for earlier 2 cases, if we are comparing all the 3 cases, we will see our degree of reaction will be having more chances to go negative near the hub region. But if you consider a variation of my degree of reaction for, say, my free vortex design, you can say that's what is, say, less in that sense. And here this is what is varying in more way. Okay, and this is what will give you idea how do we use this exponent for the calculation of our degree of reaction, and how this is what will be impacting on our design criteria. Okay, now if this is what is known to us, if we will be putting, the idea will come, you will say this design what we are discussing, where our degree of reaction at the midsection we have assumed to be 0.5. Okay, and since we are assuming this to be 0.5 for all exponent design, what we have realized, I will be having my degree of reaction to be going to negative near the hub region. Now the question will arise, what need to be done if I am looking for my degree of reaction to be positive? So this is what it says. If I will be assuming my RH by RT equal to 0.4, so you can understand my hub radius, that's what is, say, less. Where we are discussing, that's what is, say, up to tip radius, it is coming, say, lower value. Under that condition, if you are considering, say, all these 3 design concepts, if you will be implementing, it says for, say, your free vortex concept, if I will be considering my degree of reaction to be of different values, you can see if I am assuming degree of reaction to be 0.6, you can say still I am having chances for my degree of reaction to go negative. So it says at midsection I need to go with, say, high degree of reaction. Okay, it says I need to go with, say, more degree of reaction near the mid station. And that's what it says. You can assume safely your degree of reaction to be 0.8. Remember one thing, if you are considering that to be 0.8, at tip you will be having my degree of reaction to becoming very high. So you can understand we are having, or we are targeting our degree of reaction parameter for the design configurations. Okay. Now here if we consider, we have discussed about our free vortex concept. Let's come here again. So if we consider at, say, entry station, I am writing my Cw into R equal to constant, I am saying that as, say, K. And at the exit of my rotor, I will say this is what is given by my Cw into R equal to constant. Okay, if this is what is a kind of configuration what we are having, okay, and then what we know at mid station we can have our calculation. So this is what is my velocity triangle at the entry of my rotor, and this is what will be my velocity triangle at the exit of my rotor. Now what we are interested in is, say, what is happening near the tip region. So I will be putting my tip or U-tip, I will be saying that's what is my pi d n by 60. Since my tip diameter is larger, I will be having this as a configuration U-tip. Okay, that's what is giving me my relative velocity component to be V1 dash. And if you look at, that's giving me my blade angle, or we can say my airflow angle at the entry of rotor as beta 1 dash. In line to that, at the exit of rotor, I will be having the variation of my angle, that's what is given by beta 2 dash. Okay. Now we know near the hub region, again and again, we know the radius near the hub, that's what is lower. That's the reason why my U tip, that's what will be coming to be lower. And this is what will be the change of my angle beta 1 dash, double dash. Okay. And here at the exit, if I'll be putting, this is what will be giving me beta 2 double dash. Now we need to be very careful here. You can say all the way from my hub to shroud, my beta 1 and beta 2, that's what is changing. The change in this beta 2 and beta 1 is because of my change of peripheral speed. And if you are considering here, this is what is representing what is happening with my beta 1 and beta 2. So in this particular region, if you are looking at, it says this is what is a station at hub where my delta beta is coming to be large. That may be in the range of maybe 35 to 42 degree. Okay. And if you are looking near the tip region, that's where my angle delta beta, that's what is coming to be lower. Okay. When I say my delta beta, that's what is to be larger, you can understand that's where you need to have more amount of work that need to be done. And if I am considering this delta beta variation, that's what is giving us idea about what is happening in sense of my blade twist. Okay. And that's the reason we must realize my blade for free vortex design, that's what will be highly twisted blade. So you can understand here, like what all we started discussing is we have taken two approaches where we have assumed our stagnation enthalpy to be constant throughout my span and my arbitrary variation of say whirl component. And that's what we have defined in the form of say some constant, that's what is say CW1 and CW2. Then the exponent what we have in the equation for CW1 and CW2, that's what we have assumed to be n equal to 0. We have assumed that to be n equal to 1, and then we have assumed this n equal to minus 1. And if we go back, if we try to look at what is happening, say we have realized, say we will be having the variation of degree of reaction. We can say when I am having my n equal to 1, that's what is giving free vortex concept. When I am taking my n equal to 0, that's what is giving me my exponential design concept, and my n equal to 1, that's what is giving first order design concept. With this background, we will be moving ahead in order to understand what is happening in sense of this whirl distribution. So these are three approaches what we are discussing. Okay. And in next lecture, we will be discussing about what all other approaches which are possible. Thank you very much for your kind attention. See you in the next lecture. Thank you. Thank you very much.